the hydrogen is three-dimensional, and your photo is two-dimensional.
Right.
So how do you arrange it so that you can actually see the spirals in two dimensions?
You pick the right pictures to show to an audience. Here's an example where it's not that way. We didn't have it end on, and you see it looks more like a corkscrew. That's just because I'm looking at the spiral thing from an angle here. But if you think of a spiral, the spiral will get tighter or looser as I'm changing the angle a little bit, but it typically is going to look like a spiral. If I'm end on, it won't look like anything. And if I'm at a high angle, I'll get a corkscrew like that. But for the most part, it's going to give you the classic track there.
Now, are there videos also including to this for you to show a circuit, or there are multiple instances in the camera getting and then you create?
No, this is one snapshot. So these are bubbles that are formed, and the bubbles last for a little while. So the particle comes in, it makes a trail of bubbles, and I've got some time to take that picture. So what I have here is a pion has come in. Pion comes in here and creates a muon and a muon neutrino. So I've got now a pi comes in and goes to mu and muon neutrino. And in doing that, this is my muon. Muon is a heavy electron. That's really all it is. It's heavy, so instead of having a lot of momentum, instead of having a little spiral here, it's this big arc that comes through. That's the first thing I see. Now, there's like a sudden left turn there. The pion comes in, goes bam. That's a hint that I've got an interaction that goes on there. There's other things that seem like they're in the same place. That's just kind of an artifact of how it's lit up. The neutrino came off this line. I don't see it because it doesn't really interact with anything, plus it's not charged, so I wouldn't see it anyway. And there's no other evidence of it because it's just going to go through the rest of the Earth and keep going. But my pion has come in, I've created this muon. Now, a muon only lasts for a certain amount of time. It does not have a long lifetime until it decays. So it decays down here, and that's what this little short jag is there. It's the decay of the muon into, I've got an electron that comes off. I have an electron neutrino that will come off as well that I won't see, and I'll have an anti-muon neutrino because of that conservation of the lepton level there. Let's see. So this is another case where I have basically the same thing happen. I've got my muon comes around here, decays into an electron, which is the tighter spiral, and electron neutrino, muon neutrino that come off there. I can tell that something must have come off because I've got a sudden turn. I've got to conserve momentum. I can't just sit here and make a right turn for no reason. Something else has to have carried that momentum off the other direction. So that's the clue from those. And so those are sort of the basic example ones, and this is where it gets interesting. Lots of stuff happens. In this case, I had something large and heavy come through fairly quickly. It broke up into multiple different charged pieces. What I've done here, I should point this out. This is the actual photograph. You see this is photographic film. This is the track from the roll of film here that's on the side. And when you look at this, you have, especially on microfilm or microfiche, you run the thing through, you have a projector on a big white table, and you just stand there looking at the table with a way to color on the table and kind of identify which particles are where and what must have happened. So I had this thing come in and it broke up into three pieces, and then I have this little V here, which means it's short, it must be something short-lived. It's going to be fairly heavy because there's not much curvature to it. There's got to be some curvature because if it weren't a charged particle, then you wouldn't see it. And I can trace the vertex of this down and see that it must have come from here. I have things, there must be something else that I can't see. With each of these pieces, I can trace back where they came from. This guy, this pair production here, came from the same interaction as this because I can trace back and see this lines up right there. So whatever happened here shot off something that wasn't charged. And when it got here, that's when it decayed. And I can see those things happening. These big fat things, these are customers. So that's bubble chambers. That's how I can look at this and get an actual picture of what's happening. After that, it gets a little more complicated. The thing with the bubble chambers is that I have to sit there and look at film. I can only take pictures so quickly. This is an actual physical mechanical process, so I'm taking a couple of pictures a second maybe. And then I have thousands of pictures that I have to sit in a room with a pencil and kind of figure out what went where. And that's laborious, and it's hard to find something new. I also have to infer a lot from what's going on from looking at those pictures. And I can't really test ideas. If I could automate this, this would be great. It would also win you a Nobel Prize. Look at the wire chamber, or drift chamber, or the wire drift chamber that goes by different names. The multi-wire proportional drift counter, I think was the actual official name. What I've got here is a bunch of wires in a grid. And as the particle goes through, I put them in something that will create other charged particles that drift around to the wires. And I can detect something going through the grid. So I make essentially a screen like this. If my particle goes through, I can tell which two wires it went between. And if I stack them up and I alternate which way they go, I can create this, this array of wires. And so you're looking down at the wires. Your particle comes through here. And these circles are what wires saw your particle go by. And by doing that, I can figure out where the thing went. And I can build this track. And this I can use a computer now to do. I don't have to look at photographic pictures anymore. I can't look at photographic pictures anymore. But on the other hand, I know now, if I build this thing out of this stack of these wire grids, I can tell you which way the particle went and what happened and how it curved and all those things. All the stuff that I had from the bubble chamber, I now have in a series of dots on a computer that I can connect. And that was a key thing, because now I can automate this. Not only can I automate it and have computers do it a lot faster than I can also test out ideas. I can say, well, what would happen if this? And I can model what different kinds of particles would look like. I can say, if a particle, if there was this new hypothetical particle, and it had a certain mass, 100 and whatever, what would it do? I make the computer show what it would do. And then I can compare that to the data. And that comparison will tell me if what I found is what I predicted, or if it's something different. I can keep running more and more simulations of different kinds of particles, different hypothetical things, and see what matches up in the data. I can also subtract out things that I know are going to happen and only I can get rid of all that background that I had in the other pictures. I can also, on the roof of my detector, I can put another detector that looks for cosmic rays. And then if I see a cosmic ray, I can shut off the data, say, throw this one out, don't count it. And then I can screen out the cosmic rays. So instead of having that complicated picture with all the mess on it from the bubble chambers, now I have a clean picture that's only the stuff that I know didn't have any cosmic rays. Let's call it a veto detector. Then when I have those screens, I can wrap them around into a circle and make a cylinder of those wires. When I make a cylinder of those wires and look something like this. These are all the wires running back and forth. This is a particular experiment. So you see there's a guy there for scale. This is 5 meters long. The reason I need to do that is because if I have a collider, I need to be able to detect things that are going on in this collider. And I have two things that are coming together and smashing, the stuff's coming out in every direction. In the bubble chamber, that's a fixed target. I'm shooting the beam into the chamber, and then I watch the stuff spew out. But if I have a collider, I can't just put a detector somewhere and see it. Everything's going to go everywhere. So the collision happens in the center of this thing, and the particles can come out in any different direction, and then I can see them all no matter what direction they come through by making a cylinder around. And this is what it looks like on the computer here now. It's essentially looking end-on to this thing from here and seeing I had a collision in here because I know where the collisions are going to be because I made them, and I can watch all the different particles come out, and I can use the computer to track this. And so part of it is that I can automate it, part of it is that when I get to big collisions of big things, it looks like this. This is, these are big things. This is like gold on gold being smashed together with tons and tons of stuff, and a gigantic mess spews out. There is no way I'm going to sit here and with a pencil and figure out what happened. But I can do this with the computer because with this multi-wire counter, I can handle very complicated things. So when we get to the Large Hadron Collider, we get to the relativistic heavy ion collider that's in Brookhaven. These are the kinds of things that are coming out of the data. Okay, now neutrinos that we talked about for a while. These neutrinos, they only feel the weak force. I have some things that feel the strong force, leptons don't, quarks do. Then I have everything feels the weak force. And then the electromagnetic force, like things that are charged. Neutrinos are not charged, so they're not going to feel the electromagnetic force. There are, again, a bazillion of them streaming through you right now. You can't really see them in ordinary detectors. They don't show up. They really don't crash into things much at all, so I can't really find them that way. And so they don't make any other tracks. Or even in some of the bubble chambers, it'd be a neutral particle that I don't see, but then I see it make a pair, electron-positron pair. I won't see that for a neutrino because it's not going to cause the pair production. There's just not that much of an interaction there. So the other thing is that because I've got all these cosmic rays, if I'm to see one, what little it does interact, I have to make sure that I've screened everything else out. And that's sort of hard to do. I can't just look for the cosmic rays and cancel them out. But there's a rescue to this, and it's called Cherenkov radiation, which is another one of the prizes. It was given to 3 guys, 2 Jews and Cherenkov. This is based on the idea that nothing goes faster than light, right? The speed of light is the ultimate speed limit. Nothing can go faster than light. That's true in a vacuum. Once light is going through material, it slows down. The speed of light is still the speed of light, but the speed that the light goes when it's in a material is less than the speed of light. But neutrinos, that's because the light is interacting with the material, because it's electromagnetic interactions all the time. Neutrinos don't feel electromagnetic interaction. They only feel the weak force. The weak force is fairly rare or slow. So neutrinos actually don't really slow down when they go through things. They kind of go at the regular speed. That means that I have neutrinos that are going faster than the speed of light in the material. They're not going faster than the speed of light. They're going faster than the speed that light goes in the material they're passing through. When something goes faster than the speed of whatever propagates through it, you get a sonic boom. A supersonic airplane makes that sonic boom that goes through. That's because it's going faster than the speed of sound in air. So if I have a neutrino that's going faster than the speed of light in something that's transparent, water, Windex, then I will get the visual equivalent of a sonic boom. It's the same as a sonic boom from a jet, but it's from a neutrino because it's going faster than the speed of light. So what that looks like then is a cone of light that comes out. That's that bang from the jet going through, or actually the bang from a bullet, that's also a sonic boom. When somebody fires a gun, that sound, that's not the sound of the explosion, that's not the sound of the bullet, that's the sound of the sonic boom from the bullet. So you get that kind of a pop. That's what happens, but in a flash instead of a pop. And it comes out as a cone of light from this thing. So there's 3 places that's relevant. One is solar neutrinos. We talked about the solar neutrino deficit, neutrino oscillations changing from one flavor to another. That's one case where this was used. It can be used to detect supernovas because supernovas spit out an enormous number of neutrinos. The neutrinos actually get here before anything else does, so that we're able to, because they come from very early in the process, from the center of the star when it's about to explode. They don't get stopped. The light is, everything else is slowed down by the supernova process itself, or comes later. So we can actually detect supernovas before you can see them, and so go out and look up, and it's there. And then neutrino beam experiments. Anything you want to do, when you want to do an experiment with neutrinos, use this kind of a technique. The way this works, though, again, I have to screen out everything else that could happen. So I need some kind of shielding, so I bury it underground. This is the Sudbury Neutrino Observatory in Canada. This is a little less than 2 miles underground. So you dig a hole 2 miles underground. There was already a hole there. It was a mine. Then we put a ball of photomultiplier tubes, which are really just light detectors. If I get a little piece of light, it makes it, it amplifies it, so I can figure out where it went, or how much light there was, who the thing is. And I fill it with bleach or Windex, some kind of cleaning fluid, because that happens to be the thing that carries the light well, and the neutrinos will interact with most reliably here. So again, there's a guy for scale, there's a guy who's actually in a photograph. This is what the thing really looks like. These are the backs of the photomultipliers. In real life, once it's connected, each of these things has cabling on the back and all of that, so it's like a much bigger mess. Very hard to get a picture of these things because they're buried 2 miles under the ground in a small chamber. But this is this ball filled with liquid is the neutrino detector. And this is what again, these are all computerized, so this is what a solar neutrino looks like. It came through the detector, it somewhere over here made this cone of light, and what you're looking at, each of those dots is, let's see, every one of these things is one of these light detectors, one of these photomultipliers. What the computer does is when one of them sees a bit of light, it records that as a dot. So then I have the computer show me, this is that same sphere, just stretched out, and I have it show me, okay, where were all the dots? Where did all the, each photomultiplier that saw something makes a dot. And so I can see that I have this ring. So what this ring came from was a neutrino came in here. As it was passing through this way, it comes through and it keeps going. It doesn't stop or do anything else. It creates this light boom, this cone of light. The cone of light comes out and it hits my detectors here and detect that light. There's another detector. This detector actually got the Nobel Prize this year. This year's prize was for a guy working on the Super Kamiokande. And so this is in Japan. It's the same kind of thing. It's also a little less than 2 miles under the ground, mile and a half underground, in another mine. This one is a big cylinder filled with these photomultiplier tubes. And they love taking pictures of going around in boats, these things for some reason. So this was actually big enough to be in a boat, so you get a couple of guys here and they float around and polish the detectors, whatever they do. But this gives you an image of what's happening when the neutrino comes through. Again, this is the rock of the mine. The reason we need that is so nothing else but the neutrinos come through. We screen everything else out by putting it a couple miles underground. The neutrino comes in, the Cherenkov radiation, that's this light boom, comes off in this cone. The neutrino continues to go on about its business, and it leaves, that cone lights up those photomultiplier tubes. And you get this kind of a ring. Because you have that ring, you're able to tell what direction it came from. That's one of the special things about these kinds of neutrino detectors. There are other kinds of neutrino counters that can just tell. This month I got 30 neutrinos. There was one in Russia that did a lot of work. But these are special because you can tell where they came from and what type of neutrino it was. And this is part of how we do the supernova detection. And you can tell where it came from because you'll see a sudden burst of neutrinos that come through that you didn't expect, all from the same place. You can tell where they are by the shape of that disk of light that you measure in the detector. Super Kamiokande in, it was about 10 years ago or so, had an accident. There are 11,000 of these photomultipliers here. There was a crack that developed in one of them. It was not known, not noticed. During the cleaning process, and when they were refilling it with the water got about halfway up, and that first one that cracked imploded. Because it was now underwater, the water carried the shockwave very effectively, and all of the photomultipliers were destroyed or within the water levels. It was about 8,000 of the 11,000 photomultipliers. The entire bottom half of this thing essentially imploded. They cost about $3,000 a piece, so it was about $24 million worth of take to get it together. They did repair, replaced all the photomultipliers, put them all back in, and it is operational again now.
So this is just kind of a passive thing. It sits there and just waits for neutrinos to come through.
It sits there. That's true. Although now Super Kamiokande is also used, as is SNO. We've figured out since then ways to make beams of neutrinos and shoot them through the Earth. And so we have a neutrino beam from an accelerator that will come and aim itself at this thing, and we can actually do experiments with the beams. This is probably there's a bunch of these pictures, but all pretty much the same thing. A couple guys in a boat sitting in this field of things. So imagine 8,000 of these things exploding all at once. It wasn't a happy day for these guys. This is what this is what the computer output looks like from Super Kamiokande. So the neutrino came through. This is drawn where the center of it was, and you get this ring of light that comes through. And you have to account for the fact that it came into a cylinder when it was really a ring to start with. Okay.
So you should assume that multiple neutrinos or millions of neutrinos come at the same time. So
yes.
How do you isolate one?
Because they're so weakly interacting, although they're constantly coming through, it's rare for one of them to actually interact with anything. You see it. The interactions are not common. So of the bazillion that come through, 1 out of 100 bazillion will do something. So you don't really have to isolate them, they're just rare enough that they interact, even though they're common particles. That's why that day-night effect of seeing the neutrinos coming from the sun, you pass them through the entire Earth. Most of them go through the Earth unchanged, but just enough of them are modified or interact with the material of the Earth as it goes through that you're able to see that difference. But it's got to go through the entire Earth just to have any kind of a chance of any interaction at all. So that's neutrino detection. Then there's a couple of kinds of more kind of normal particle detectors. These are composite detectors now. So we talked about the bubble chamber, which was an early version, the string chamber, the wire chamber, which is sort of an automated version of a bubble chamber neutrino detectors. The way we really do things are either at a fixed target or with a collision experiment is by making a composite of a bunch of different kinds of detectors. The idea here is we're trying to sort everything out. Now we've moved to a thing, in the bubble chamber days, you look at the picture and you look for something that looks interesting or you haven't seen before, or you're just counting events of a certain type to figure out how often something happens. But you're kind of looking at known stuff. And you're ignoring everything that's not the thing you're looking for. We've moved then, when we get to the real accelerators and more modern experiments, we want to just see everything that happens and measure it all. So the way we do that is for any interaction, we try to identify everything that happens. We screen out things that we know are not interesting, but for the most part, so sometimes we're focused on a particular type of interaction, so we'll only look at the events we're interested in, but really we need to identify everything that happens. So we build these composite detectors. This one is called KTEV, for kaons of the Tevatron. It was designed to study these guys and the matter-antimatter asymmetry in the universe that I talked a little bit about last time, why we're made of matter and the universe didn't just explode itself. So the Tevatron is the accelerator at Fermilab because it goes to 1 TeV of energy. Actually got up to like 997 or something, 0.997 TeV. The Tevatron was then the machine that makes the beam. There's stuff up here that creates kaon beams, or a kaon beam, and then as it goes through different sections here. There's a set of drift chambers, which are those wire chambers, to see as the kaons decay, what they're decaying into and which way it goes. We have a calorimeter here, which measures the energy explicitly of each of these things. Or from the curves in the tracks, I can figure out their momentum. That doesn't necessarily tell me the energy. So calorimeters, just as a regular calorimeter would to measure the calories in your Big Mac. They don't use the same kind of calorimeter, but it's really just measuring how much energy is in each of these particles. As I go through, I'm screening out different kinds of particles. I have on the roof of this thing the detectors that screen out the cosmic rays, and then this big black thing is, I need something that's going to be able to help me determine which things are electrons and which things are muons. So I need to screen out the electrons and let the muons go through. Electrons are light, so they're not that hard to stop, but I need something that will stop one and not stop the other. And it turns out, what you want to use is what's cheap. A lot of these things are just, what can I get? Battleship steel turns out to be the thing. So you take an old battleship from back in the day, cut it into pieces, pile up the steel, and make a giant wall of steel. So as you're walking past this detector, you go through all these different things, and then there's this massive wall of steel, and on the back of it is a bunch of detectors. If I detect something behind the steel, it's got to be muon, because nothing else would have made it through the steel. It was a neutrino, it wouldn't interact anyway. I won't detect it. So the way I detect a muon is by screening everything else out, and left must be a muon. I also have along here these veto detectors, which allow me to exclude anything that's coming from the wrong direction or is not part of what I was looking for in the first place. So if the veto detector triggers, then it's not. This is what it looks like in a couple different views. This is what it looks like if you're actually there. These are the different chambers, drift chambers, that again are just allowing me to figure out which angle these things are coming at. This is again the same picture, but instead of being just from the side view, it's a 3D picture. So my beam is coming this way, my kaons are decaying, I'm looking at the decay products as they go through, and I'm figuring out with that stack of different kinds of detectors which things they are. And I can figure also from, it's called the kinematics, but the amount of energy and momentum in each direction, what decay process it went through. So the beam in this case is coming from here. This is the case in Fermilab where it's going around the ring, it goes around and around and around, and then it spits off one of the side. It's a fixed target experiment, which is why it's shaped this way. With the beam coming in, hits the target, and goes up. The way this works, okay, so in practice, this thing is 200 meters long, that picture on the last page. So it's, this whole thing is 200 meters. It's fairly big. The proton beam, or the accelerators make the protons, I have to make the kaons first, so it hits the target, I make a bunch of kaons. The problem is I'm also going to make a whole bunch of other stuff, so I have to sort out just the kaons. So I have a big area here of about 100 meters where I get rid of everything that's not a kaon. And then I have a region where the kaons are going to decay. Remember, I know how long they live, more or less, because I'm studying them. And I have to account for the fact these things are going fast. Because they're going fast, they're going to live longer because of relativity. Relativity will make their time slow down. We'll talk about that next week a little bit. And so I have a bigger region over which they decay. Even if they last only a tiny amount of time, they're going to live longer because they're going so quickly. Then when they decay, they mostly decay into pions. We had a couple examples of that earlier. And then just watching what the pions do will tell me what goes on. So that's over the course of that 200 meters. This is what it looks like from the computer plot here. It decayed. This was a decay where I went to 2 pi0 particles, which then decayed themselves. So I've detected these 4 tracks here. This is my wire chambers. These are the calorimeters that have measured how much energy each of these things had. So this is kind of looking down at the beam, the things coming at me, split apart, and I watch those tracks. And in this case, this is the same thing. It's just looking down from the top, and you can see. Again, the 3D view is necessary because in this case, 2 of them would have overlapped, where I was just taking a picture from above. This is all done by computer. There are many, many of these events that you go through and process, sort out which ones are which ones count, which ones don't. And an example of that was with the bubble chamber, I'm taking a couple of pictures a second and looking at them by hand. In KTEV, each second that this thing ran, and it ran for a year and a half, each second that it ran for a year and a half, there were 200 billion protons that hit that target, and 500,000 kaons that were produced every second. I'm looking at kaon decays, I'm looking at 500,000 of them a second. About 10,000 of them were good enough, which meant I collected all the information that I needed to there. And then, as that's running, I'm screening out as much data as I can. So I sort out only the ones that I know are actually kaon decays, because I can't record everything that happens, because that would be more than I have storage for, and faster than I can actually write it to magnetic tape. So about 2,000 a second are recorded. Then I go home after my year and a half of running this experiment, and I have an army of grad students, and now giant rooms full of magnetic tape. And we spend the next 4 years or so reading those magnetic tapes, running computer simulations, and figuring out which of those events are which. After the basic level of offline analysis, there's about 10 of them from each second that were actually decays of a kaon into 2 pi's that you do afterward. Then once I have those 10 per second, I start looking at the details there. That's where it farms out to the army of grad students to do all their theses on exactly what happened here, what interesting things they were looking for in this kaon case. So that's a lot of data that can only be done that way. I'm going to stop in a moment here, and we'll pick up next week with a little bit. I do want to talk a little bit about what it looks like in a collider. Similar idea, but a little bit different. And tease you with some pictures of the collider. We'll talk about the discovery of the top quark. This is where I now have the proton and the antiproton coming this way. They collide. I can make much, much bigger things because a head-on collision is much more powerful than punching through a target. It's also much, much messier, so the detectors get more interesting as well. We'll pick up with that next week. We will also then talk, next week's our last week, so we'll talk a little bit about relativity and see what general and special relativity are. It's a little bit different than most of the rest of what we're talking about, but it is more or less modern physics. And critically important for all these processes, as well as for your GPS working and things like that. So we'll talk about relativity, and then we'll probably, if we have a little bit of time at the end, we'll just say a few words about quantum mechanics. That's its own whole world of crazy stuff that nobody would believe anyway. So we'll introduce that, and then we'll finish for the semester. See you next week.